Now we're going to hear from Chris Grove and Scott Smith from Nozomi Networks. They're going to be speaking about using AI to precisely detect anomalies in the OT process. Chris comes to us and he brings 25 years of cybersecurity experience with a deep knowledge of IT and OT in IoT networks and mission critical infrastructure. His prior experience includes managing large, critical, and complex security projects around the world for customers of leading IT and OT security vendors. Scott is a senior product manager at Nozomi Networks. In his role, he's accountable for working closely with key customers to assist with helping solve cybersecurity challenges by evolving the Nozomi solution. Scott spent 8 years working with large electrical utilities supporting devices in the EMS and DCS environments. As Scott worked to help his organizations meet NERC compliance and enhance its cybersecurity posture, he noticed gaps in available products, and then he transferred from the customer side to the commercial side and into his current role at Nozomi. So Chris and Scott, thank you for joining us, and I'm looking forward to hearing what you guys have to say. So thank you very much.
Thanks, Don. Good to see you again. And really awesome to see so many familiar names here again this year at SANS, as well as so many new names. So definitely a lot more people. I agree with the statements made earlier about the growth in our space, and it's amazing to see that. So thank you all for giving us the time to talk about something that is pretty exciting, I think. Artificial intelligence and using that to detect anomalies in the process. So I'll do some slides in the beginning and just kind of set the stage and talk about what AI is and our approach to it. And then Scott will sort of show the fun stuff and bring in a demo and use some live stuff. So first, what is driving the market to even talk about AI? It's being used in a lot of products. It's a buzzword that's being thrown around sometimes a little loosely, and sometimes it's really well baked into a product. So I'd like to start with just a brief definition around exactly what AI is and what it isn't. Essentially, it's just a loose term to define a science that basically enables computers to make intelligent decisions based on having more and more information in them. And if we look at it in the context of why we would even consider something like that, we have to look at the problem. And if you, from our perspective as like a product company that's making a solution, we're looking across all of these different types of enterprises that have, although similar equipment, the products that they're making are quite different, and how that equipment's being used is a lot different. And a lot of the use cases are different. But the equipment is sort of the same in some of them. The risks are sort of the same. So as many differences, there's similarities. And I think if we just look at who's on this call and who's been attending the SANS training, we would see that we come from all these different sectors here, and yet a lot of the brands that we use are overlapping, and a lot of the threats that we're talking about today is basically the same. So it only makes sense to find a solution that's going to work across all these different things, but the nuances of them make it very complex. So the difference between, making cereal and controlling an airport and manufacturing oil and gas and distributing power and so on is what really adds a whole dimension of data and complexity to solving the problem. Hence AI. And that's why some companies are really embracing AI to help us solve some of these cybersecurity challenges. Why are they becoming more challenged today than they used to be? Well, the digital transformation that's happening at the plant level is adding a lot of new technologies to the mix that aren't necessarily being accounted for or being managed the same that we've managed other risks along the years. IoT devices have also really exacerbated the complexity of the problem. Juniper saying that by 2024, there's going to be 83 billion IoT connections. Some of those will be in our homes, some of those will be in our businesses, and in our IT enterprises, our OT enterprises, pretty much everywhere. And to make those even more difficult to think about, enter 5G, meaning that a lot of these devices around us doing things for us may not even necessarily be on the networks that we're used to talking about today. So we may have a factory made of, or not even just a factory, any kind of an OT environment where different devices are using different types of networking and different types of technologies to do different tasks. So the future isn't about being simplified, it's about becoming more complex. So we have to use more complex tools to take on the cybersecurity challenge that's going to arise from all of this new technology really being mixed up together. Also, our threats are also getting more sophisticated. Being able to mitigate the risks that they're bringing, the way that they're attacking systems, getting into supply chains, infecting systems that we used to believe for decades were secure. The threats are definitely getting more sophisticated as well. So we need a better set of tools to handle all of this stuff before we really get there. A lot of it is present today. Some of it is there that we don't really even know about yet. And then another driver that is pushing companies to start embracing AI is the high cost of incidents. If these things didn't really do any damage, if the attackers weren't really affecting anything, then there would be no need to develop these high-end sophisticated tools to chase down the things in the network that don't really belong. And it goes well beyond what's on the network. It also goes into how the systems are behaving, when and where, how it's using which type of a protocol, and also the OT process itself. Are the parameters and set points being used in coordination with how we thought it was supposed to be used or how it's been used in the past? So these can get very complex and really sticky in all the different environments that we would come across. So one of the things that when AI and machine learning terms are sort of thrown around is what exactly is it and what does it do? So to just generalize AI again, it's really about the science and the engineering of making intelligent machines. But the machine learning component is about using these machines and teaching them with more and more data. So the more information you run through it, the smarter it gets. And that's quite different than using logic or the way that we've approached solving problems in the past. And I'll demonstrate that in just a second. So we're only going to focus on two small parts of AI for a few minutes here, which are the machine learning and data clustering. And I'll specifically touch on something called neural networks, and then also briefly on expert systems and what they bring to the table. So the end more, if you're interested in further reading about AI and how it really is going to map into the future, they have this thing called the AI roadmap. And again, we're just talking up here at this like machine learning, and I'm actually going to give you an example at the image recognition tree here, but you can see where AI is sort of going into the future to bring together everything from learning about information that's being taught all the way to robotics, speech, and vision. So it's quite a big science that encompasses a lot of things. So when you see a product that has AI included on it, it's really good to understand exactly where and what is the benefit of having that there, because it's a easy buzzword to use. And if we look at how AI might be used in practice in computing, hopefully you'll be able to see this okay. We're looking at a Tesla that is using AI to automatically drive a car and swing around a corner, pull up to a stop sign, and make a decision about whether or not to proceed into an intersection with traffic. And there's so many decisions being made there. In the bottom right, you can see something that the AI would need to pay attention to, and that's what? Is it a cat? Is it a truck? A tree? Then is it in motion? It needs to know what direction that motion is, how fast it is. Is it really pertinent to where I'm going? There's so many facets of information that need to be learned, not just about that box truck, but about pedestrians, mapping, and so on, that the vast amount of data becomes overly complex when you try to use simple logic to accomplish those goals. So to simplify that, let's just talk about an easy task. Let's try to determine if that's a sea bass or a salmon. So if we used logic, we could think, well, let's use some characteristics like color or shade, and we create a bunch of if then or if then else logic use cases or cases of ways to process the information to try to get there using what we've always been taught about computers in the past, which is using this way to solve problems. But if we started to chart that out and we started to look at the two characteristics, the width and the lightness of those two fish using logic, and then we applied them to a chart you can see on the right, there's going to be outliers. And those outliers sort of prove that logic false. And what typically we would do is start to add more logic to fix this problem. Some of these salmon aren't sea bass, and yet there they are in the sea bass category. So if you look at this curve here that's sort of highlighting all of these outliers, that is a challenge when you're using logic in something like cybersecurity, because all of those outliers end up being a false positive and an alert of some sort that someone has to attend to and pay attention to. And that's probably the number one source of alert fatigue, is chasing these outliers and things that maybe sort of look like they belong, but they don't quite belong because the logic is triggering an alert that may not necessarily have needed to be triggered. So if we were to use two characteristics here, AI would be the science of creating this curved line and being able to learn that these are indeed salmon, even though these two characteristics are putting it in that category. And if we start to add another dimension, a z dimension to this, and add length, and then maybe even beyond a z dimension, other dimensions, and start adding in all kinds of other characteristics like weight, color, dorsal fin type, teeth type, and maybe thousands of other characteristics, we can put so much information through that model and automatically arrive at the conclusion of if it's salmon or sea bass, and we will be right almost every single time. And if it's wrong, when we correct the model, when we correct the data, the conclusion made, the model, the AI will learn from that and it'll improve on its behavior the next time. There was no reprogramming of the actual logic behind it required. Just running more information through that enabled it to make better decisions in the future. And there's a data set that was released by the United States Postal Service back in the 90s. And it was kind of a challenge to figure out how to automatically read these digits that are written on envelopes. And it's not just easy to, apply OCR and read them, because there's so many variations of how people write. And there's also so many variations of how people put addresses on an envelope. So OCR was quite a challenge, and it got there, but it was, again, very high rate of false positives and very high error rate. So they needed to improve it. So what they did was they published this, and it's got 5,000 city names, 10,000 zip codes, 50,000 alphanumeric characters, and so on. So it's a perfect data set to use AI to solve a complex problem. And what we use is what's called a neural network. And these are basically functions here. And in this case of the United States Postal Service data set, we could identify 784 characteristics of what a number might look like. And using those characteristics and then other characteristics, each one being a different input neuron in this neural network, we would be able to look at a digit like a 2, look at characteristics, move to another set of characteristics, and arrive at the conclusion at the end that that's a 2. And then if we see a 1, we can arrive at the conclusion that it's a 1 based on the characteristics of it and having run data through it. If somebody comes along and writes 1 slightly different, we can still get to a 1 without reprogramming the logic. And it sounds like AI is like an end-all magic silver bullet to everything, but it's really not. It is a tool meant to be used alongside a human. It's not going to do all of our work for us. So what's amazing about humans is we can generalize instantly. A baby can look at a cat and know after seeing one cat that that's a cat. It doesn't need to see a million cats to know what a cat looks like. But if you show a baby or even a human, an adult, a million cats and ask it to find the one that's different, then that becomes quite a challenge. However, machines are quite kind of the opposite. They're great at finding that one cat in a million cats, and they're really good at processing millions of cats. But until it's seen millions of cats, it's going to have a hard time identifying the first cat that it's ever seen. So the human and the AI really needs to work together in order to get to the end result. So AI is not really the one thing that's going to do everything for us. So if we look at the evolution of where AI has come in just a very short period of time, you may remember back in the 90s, Deep Blue and chess playing versus Kasparov. That AI was purpose-built specifically not for chess. It was built for Kasparov. It only, from the hardware, the software, and all the data put in there, it only really was designed to play against one person. My 6-year-old who's learning to play chess could have possibly beaten Deep Blue simply because it was only designed to play against a single person. But in 2016, there was another generation of AI that was used to play a game called Go. If you're not familiar with it, it's apparently many multitudes more complex than chess, and it's also more difficult for a machine to defeat due to the way the game is played. So not only did AI learn how to play this more complex game and beat the champion, but it also learned how to play other games as well. The next generation of that AI went on to play not only chess, but also Atari games. And then the generation after that went on to learn how to play games without even being taught the rules, simply by watching the game being played. So AI has really come a long way and has been able to get us really far. Unfortunately, the attackers know that as well. There's been a few incidents that have already happened out there, and we're saying that these are AI powered attacks because in one various component or another, the attacker leveraged artificial intelligence to make their attacks either faster to get in, they were able to get deeper into the system because they could process data quicker and pick targets better, or they were able to pick places that they were going to get better persistence to stay in the system longer, or they were going to be more accurate in what they hit, or they were going to know exactly if they needed to touch something, where to find it, and what was going to be the most damaging. So typically all of those operations in a cyber attack, beyond like the initial infection, a lot of times there's going to be a manual operation involved as well. So they're also interested in speeding up and lowering the cost on their side, and AI gives the attacker just as much benefit as the defender. So we can choose to like not embrace it. The problem is we're going to be forced to at some point because the attackers have already started to move there. And something that's thrown around AI circles quite often is this term that there is no AI without IA. And that's basically, you can't get there in AI without having a solid information architecture. And that basically means that you have to start from the beginning and bake that into your product at an early stage and build everything else upon that information architecture that was designed around neural networks and those functions, rather than using logic to solve things the old school way. So it's not really something you can bolt on because it became more popular. You really have to have embraced that very early on in the product's development and sort of held that mantra throughout the development. And there's quite a few products out there that do this very well. And some of the goals of these cybersecurity products and other products out there that are looking at IT, IoT, OT, etc., are basically the same. We're all trying to identify all of the devices in the network. Different products out there are going to be focused on different areas, and some products have much wider scope than others. Some of them are able to assess the risk and the vulnerabilities and also detecting threats and things. The point is, this is a vast amount of information, and there's a vast amount of different types of assets that all of this is applicable to. So parsing through all of this and finding things that don't belong at all levels of the network and all parts of the network and all parts of technology are really, really a sweet spot for artificial intelligence to operate in to help us get through all this. Because we all know that, using the tools to get through the alerts and to do a lot of the operations behind identifying these anomalies is something that really can be automated very well. So I'm going to pass it off to Scott just in a couple of minutes here. And some of the things that he's going to touch on are the areas in which we may find anomalies. So if we think about how our enterprise is laid out from the IT side all the way through to the OT side and all the many factories and so forth, seeing something new in that enterprise is an anomaly. And seeing something new talk to something else, or something that we've already known about talk to something else in a way that we didn't know about before, could also be considered an anomaly. Well, it is an anomaly. Whether or not it's bad or good is still TBD, but the point is that it needs to be accounted for. But do we really need to raise a red alert at the SOC just because of a new or something that wasn't quite there yet? So being able to get through all the information without raising an alert for every single thing that happens is really the objective of what AI is going to try to do. Also looking at connections between things that were there before. If they switch direction, that's also something that would be considered an anomaly. Or using an existing protocol in a different direction, as well as a different protocol. So for example, if I have an HMI that normally talks to a PLC using protocol A, and all of a sudden I see protocol A being used differently, or I see protocol B being used, those would both be considered anomalies that I would want to account for. And then an operation within a protocol. If I usually see an HMI reading values and parameters and set points, and suddenly it's writing one, I would probably want to be aware of that from an anomaly detection standpoint, and I would want to think about it, but what I would necessarily want to alert on that. In some cases, yes, in some cases, no. And the flow rates of these, when they slow down, if suddenly the HMI stopped sending a particular value at a certain rate, or it's sped up faster, or the actual parameter being set is outside of a particular range that I would expect. In a large OT environment, all of these different data points, or if you can think about that salmon and the sea bass, that chart with all the dimensions of data that we might be looking at, all of these could be also dimensions of data that we would want to analyze and consider when we're looking for problems on the network or in the process. So if we think about anomalies, it's something like an infection that came from the outside, maybe some ransomware or a piece of malware that got in. That's one type of an anomaly, which would be something connecting to someplace overseas, for example, or an industrial protocol that's leaving the corporate firewall. Hopefully that's not happening too often, but that would clearly be an anomaly. And then there's more difficult ones to find, which are ones that really exist deep inside the network, and you don't always know. They might not even be infected. Sometimes it could be either a compromised or a negligent insider. It could be something that infected another route other than needing a command and control or a connection out to the front end. So there's a recent incident that happened at a water plant. There was TeamViewer used on an HMI that everyone was aware of, and it was a IT or an approved piece of software. It was a communications channel that under normal circumstances may not have been an anomaly to the operators. However, the usage that day to set the parameter within the OT process was an anomaly. But if we were looking at the corporate firewall level for anomalies, we may not have seen that. If we were looking in various other parts of the enterprise, we may not have seen that. But deep inside of the OT process, the length of the value set as well as the range both would have been considered an anomaly if they were being inspected. So I'm going to pass the mic to the most exciting part of the show, Scott, to show some of this stuff in action. And keep in mind, there's various components and various aspects of AI behind the scenes helping process very large amounts of data in some cases across a multitude of plants. So let me stop sharing there. And Scott, I think you're in control there. There you go, Scott.
All right. Can you see my screen, Chris?
Yes, sir.
Everything looks good. All right. So looking at this, Chris mentioned many items around being able to detect anomalies and being able to do the machine learning. So let's go ahead and start looking at some of it. So right now, we first need to create a baseline, right? We need to know where we're starting from to be able to detect those anomalies. So I'm going to run a PCAP here, and we're going to start creating that baseline to know what those behaviors are. So when we see packets come in, we're looking at the source and destination, and we're starting to build that map. We're going to start, each asset is going to have their own network baseline, which then we can be able to detect anomalies from that. So we're looking at the source destination, and then we're going to look at the protocols. Is it a known protocol? Is it something different? Is it meeting those specific standards? So we're going to look at the header size. We're going to look at the different protocols being used, what's inside those packets, to be able to see if there's anything abnormal within those. Once we do that, we're going to start building that network baseline. We can see here we're starting to learn more and more as it's coming out. So each network baseline is being learned and more traffic is coming in. And I'm going to shorten our learning period for this because we probably don't want to stay here for 30 days waiting for everything to learn. So I'm going to speed stuff up, and we'll start showing some anomalies in here. So I'll let it run for a minute here, and we can look at some data in the meantime. But we can start seeing some different traffic coming in. So we can see like some Ethernet IP. We can get some more information around that to be able to see what it's bringing and taking out of those packets, which is inside of that network baseline. So we can see the source destination. We can see which zones they're coming from. We can see the handshakes and attempts. So this is all part of that network baseline that we're building together to understand better what's going on within that machine. We can see the different function codes being sent, which is one of the key items that Chris mentioned, is being able to see if there's any anomalies with different function codes. So we know from this 162.22 to 1.28, we see these function codes that have been sent via Ethernet IP. After that learning period, if there's any new function codes being sent to it, it's going to go ahead and let you know. It's going to go ahead and alert you and say, hey, this is not a function code that was previously learned in that baseline. Now, if you have a group of like PLCs or like devices, they all have these same function codes, and one comes in the network, it's going to automatically learn that and say, hey, this is the same firmware, this is the same device. We're going to go ahead and learn those same function codes as we see them come in, because you've already approved it for maybe 30 other devices, and this is a new device coming online. So we'll go ahead and eliminate some of those alerts and manual effort and go ahead and learn that because you've already said that those function codes are approved. So trying to speed up that learning process and eliminate some of that alert fatigue. So let's see here. I think we have a pretty good baseline of what's going on. So let me throw some attacks or some different stuff going on. So before I do that, I guess, we have the color codes here, which we can see the producers, we can see the historians, the consumers, and so forth. We can see those color coordinated. I'm going to go ahead and change those to make it a little bit easier. So I'm going to start looking for not learn nodes, so new devices on the network. And I'm also going to change this to not learn links, so new communication links, just to make it a little bit easier for this demo. So let's go ahead and start an attack here.
We're kicking off anomaly detection with 1 minute of learning on this plant.
Yes, just about a minute we're gonna of learning, and the whole time we're gonna try to see some differences in this. So as it runs through the PCAPs, it's gonna start doing the DPI and start analyzing what's new and what's different from it. So right now, it's just having the same PCAPs going through. We haven't had anything really new that's changed or different within that. But we can start to see maybe some different assets coming in. So we can see We've got 154 learned assets right now. We have 0 partially learned and 0 not learned. So we'll give it some time here. I see some links coming in that are showing up as yellow. So we're starting to see some new devices. We can definitely filter on those to be able to see this device a little bit better, or we can see it holistically, how it fits into the full network. Let's narrow this down a bit here. So we see between these two devices, we see some partially learned links and some devices that are, looks like it's talking S7. So let's go ahead and look at some of this data. So if I click on the link here, I can see that now my baseline is slightly different. So I have a yellow gear that says things have changed. So this is something that is different. This is function codes, some starts and uploads that were not previously learned in that baseline. So we can see there was a setup communication in that 1 minute that we ran this PCAP. We had a setup communication, a function code 240 sent. And then after that, I started doing some starts and stops and uploads. So I can see some differences within those protocols, or differences in function codes being sent in that protocol. I can, from this screen, I can go ahead and learn those so they add it into this baseline. But also, not everyone's going to be looking at the graph. Not everyone's going to be staring at a graph here and looking for those differences. So we also generate those alerts. So I've got many alerts here that have been started. So we have some man-in-the-middle stuff that was part of this attack and different changes to it. But if I look at maybe the suspicious activity, and then the two assets that we have was the 31.101 and the 31.10. Those were the assets that we looked at on the graph here. If I click on that, I can see those same function codes that we just seen that graphical view, all listed here in individual alerts. We can grab those PCAPs from it, so we can go ahead and download the PCAPs from it to be able to get further analysis. Or we can just go ahead and say, yep, this is normal. We are adding it to as part of a change, and we can go ahead and approve those. So we can see all the differences in here. So we can see the communication. We can click on it to be able to see that function code and get more details on it. So this is a difference in an individual baseline with a new function code or new communication being sent. Another item that Chris was explaining was around the process variables. So as a packet comes in, and depending on the protocol and what's in it, we're grabbing the, I'll go ahead and change this again. We're going ahead and changing the, and looking at the individual process variables, those digital values coming from maybe the PLC back to the HMI or the controller. We're looking at those values and we're putting them into a format that we can start learning. So we have some pipe flow data here. We have some speed data that we can see. We can see the number of changes that have occurred in the last couple of minutes since I started this PCAP. And we can go ahead and see what it's learning. So let me grab one that's got more changes to it here. Let's see this one. Yeah, this one for the last couple of days, it's been pretty stable. This PCAP, it's been pretty stable. Let's see if we can find a good one here that can illustrate this. So over time, over the course of a minute, it's going to be a little bit harder to baseline this and understand the normal because this is changing. So this is the flow within a pipe, and we can see some spikes and decreases within this. Over a course of maybe a couple days, a week, 30 days, we're going to be able to see patterns within this and start adding that together, which Chris was explaining, where we're going to start grouping all these spikes and group it together to be able to know what's normal or not normal. So we can see, just kind of looking over here, that just about over 15,000 was our peak. But then it also goes all the way down to 0. So we can see some flows that are coming in pretty fast, and then it goes ahead and slows down to a 0. But then maybe over time, we see this go a flow to maybe 20, right? 20,000. That's going to show that we're going to generate alerts saying there's an anomaly in that process flow that you need to take a look. There's more water, there's more chemicals going through that pipe than was previously learned in those 30 days. Or maybe it stays at 0 for a couple hours. Maybe there's no flow at all. which in those 30 days we never learned. So being able to group all those baselines together, all the behavior together, those spikes and drops, and being able to create a baseline and a pattern that we can detect and help you predict failures or making sure the machines are operating optimally. So this could be flows, this could be volts, it could be just starts and stops of turning on and shutting down, being able to create those baselines. Many other alerts in here. So I won't go in detail of all of the machine learning that we have within the product. No, we're getting close on time. So if you guys have any further questions around our AI or how Nozomi goes through and creates the different baselines and what other types of anomalies we can detect, please jump over to our Slack page and ask some questions, and we'll be sure to answer those for you.
Yes, and Scott, there are a few questions in there. It looks like I'm getting ready to answer. Chris, do you have any final thoughts, closing out thoughts that you wanted to?
I did want to remind the viewers that if they download our slide deck, there's some further information that they can reach at the end of it. There's a couple great pieces of collateral that they can take home. There's a solution brief, our new OT/IoT threat report, which has some pretty interesting findings in there, as well as a white paper on advancing your visibility with our solution, and a preventing equipment failure white paper or use case.
Well, thank you very much, both of you, Chris and Scott, for talking about that and kind of filling us in on the background for AI and how it's leveraged. It's there's a lot of data coming through some of this stuff, so certainly that learning is pretty unique, and understanding how it's all built and plays a role is important. So thank you for kind of outlining that for everybody.